Okay, note 6.14, and you are going to learn two more rules for finding derivatives quickly that are very useful. The first one's called the product rule, and the second one is called the chain rule. So the product rule is when you want to find the derivative of two functions that are multiplied together, that you could separately find the derivatives of each of them, but altogether we don't have a nice rule where we could find the derivative yet. So here would be an example. If y equals x squared multiplied by sine x, well, we know how to find the derivative of x squared. It's 2x. And we know how to find the derivative of sine x. It's cosine x. However, y prime does not equal just finding those two separate derivatives and multiplying them by each other. Okay, so then how do we do this? Well, we need to develop something called the product rule. So basically what we have is two functions, right? So we could think of it as one of the functions is f of x and it's x squared, and the other function, g of x, is sine x. And we want to find the derivative of f of x multiplied by g of x. That's what we want to find. Find the derivative of this product of two functions. And we just talked about that it is not going to be just finding the derivative of f and multiplying it by the derivative of g. That's not how it works, unfortunately. So we're going to come up with something called the product rule. We're going to use the formal definition of a derivative to develop this. And if you recall, the formal definition is the limit as h approaches 0 of a function that we want to find the derivative of, right? So if we want to find the derivative of f, then we would say it's f of x plus h minus f of x all over h. All right, well, the function we want to find the derivative of is not just f of x. It's a product. It's a function f of x multiplied by another function g of x. So using that, we're going to plug that into the formal definition and then simplify and find the limit to see what we come up with. So that would be the limit as h approaches 0. Okay, so now my function is f of x times g of x. So when I evaluate that at x plus h, I just plug an x plus h into this x and an x plus h into this x. So I would get f of x plus h multiplied by g of x plus h. Okay, now I'm going to leave a big space here because I'm actually going to need a trick that's going to happen in a second. That's why I'm leaving a big space. However, what would come next is that we would then subtract the function itself that we're trying to find the derivative of, right? So it would be minus f of x times g of x. That's what we're trying to find the derivative of. And this would all be over h. All right. So as it is right now, there's nothing I can do to find this. If I were to use direct substitution and its h goes to 0, so I would replace all the h's with 0. So it would be f of x times g of x because I'd replace that h with 0. And then there are no h's to replace with 0 here. So it would be f of x times g of x minus f of x times g of x. That's just going to give me 0 over, remember I'm doing direct substitution, so h is 0. So this would just give me 0 over 0, which is the indeterminate form, which means that your method of finding the limit is not working. So we're going to have to come up with something else. And that's where this trick comes in. So right now, I can't manipulate this algebraically in any way. However, if I add two terms in here, I will be able to do some sort of a factoring technique to figure it out. So the two terms that I can't just add something in because that would change the quantity and it would change what I'm doing. But if I add something in and then right away subtract it out, then it's like a very fancy looking 0 that I've put in here. And it just so happens that this trick of adding in f of x plus h times g of x, and then right away subtracting it out, actually, adding it back in. So here's me adding it in, and here's me subtracting it out. f of x plus h times g of x. Almost gave myself enough room to not squish it in, but not quite, but that's okay. You can see right here, these two things I put in, that's 0. That's a very fancy looking 0, but that 0 will allow me to actually find this limit. So here's how. Okay, so if you just take the first two parts, and I'm going to highlight that to show you what I mean by the first two parts. You can separate, what I'm going to do is separate this fraction. So I'm going to take this first part here and place it over h, and then I'm going to add it to this part over h, so that I basically then have two separate fractions. It's like saying, let me show you with some numbers that would make this seem easier. So if I had, for example, 1 plus 3 over 20, right? I could rewrite that as 1 over 20 plus 3 over 20. You can take the numerator, which is being added or subtracted, and as long as it's over the same denominator, split it back up. What was it before it was added up together? So that's what I'm going to do. So we then have the limit as h approaches 0, and I'm going to deal with all of this. So I'm going to split up my fraction. My first fraction will be f of x plus h times g of x plus h minus f of x plus h times g of x. And this is all over h. Okay, that's my first fraction. Plus, my second fraction is this part, all over h. And that fraction is f of x plus h times g of x minus f of x times g of x. And it's all over h. And again, we're taking the limit as h approaches 0 of all of this. Okay, so now I'm going to work with each of these by doing some factoring. So if you look at this very first fraction, what we have in common in the numerator is both terms have an f of x plus h. So what I'm going to do is factor that out. So we have the limit as h approaches 0, and now I'm going to work with the algebra of this. I'm going to factor out, let me highlight what they have in common. Both terms have an f of x plus h in common, and so I'm going to factor that out. So factoring out f of x plus h, then what that's going to leave is g of x plus h minus g of x. I meant to write g of x, there we go. Okay, g of x plus h minus g of x over h. Okay, so that's what I have right here. Then plus, okay, let's look at this fraction. What could we factor out of this fraction? Well, both terms in the numerator have a g of x in common, and so we could factor the g of x out, and that would give g of x, right? And then behind it would leave f of x plus h minus f of x. And this would all be divided by h. Okay, so now we're actually ready to go here because you can see the limit as h approaches 0 of f of x plus h, well, let h go to 0, would just be f of x, right? Because the h goes to 0. Times, look at this one, the limit as h goes to 0 of this part. Well, that would be the limit of as h approaches 0 of g of x plus h minus g of x over h. Well, that's the derivative of g of x. That would be g prime of x. Plus g of x, letting h go to 0, well, there is no h here, so it would just still be g of x times And then this part, let the limit as h goes to 0 of f of x plus h minus f of x over h. Well, that's just the derivative of f. And this is how you find the derivative of a product. If you want to find the derivative of two functions multiplied together, f of x times g of x, then the formula is here. You take f of x just as it is, multiply it by the derivative of g of x, and then add that to g of x as it is. Don't take its derivative or anything, but multiply that g of x by the derivative of f of x. So it's the first times the derivative of the second plus the second function times the derivative of the first. So let's go back to that example. Right, so here you can write it out these two different ways. F prime of x times g of x plus f of x times g prime of x. Or if you say the derivative of a function u times a function v is u dv plus v du. That's just another notation. But here's that example that we had. Okay. I did my way. There we go. Sorry, guys. So our first, if you think about it, our first function would be x squared. So we'll say f of x is x squared. And our second function is the sine x. So g of x is sine x. Then the derivative of f of x would be the derivative of x squared, which is 2x. And the derivative of g of x would be the derivative of sine x, which is cosine x. And using the product rule then, dy dx, or y prime, would be the first function times, which is x squared, times the derivative of the second function, so times cosine x, plus the second function, which is sine x, times the derivative of the first function, 2x, so 2x times sine x. And that is how you find the derivative of a product of two functions. Pretty useful. Okay. Next, there we go. So now we're going to talk about different ways of finding derivatives when you see them, because at this point, you know, sometimes it's going to say, hey, this is a problem. Use the product rule to do the derivative. Or here, find the derivative of this function. Use, you know, this method. But most of the time what happens is it just says, find the derivative. Or you're trying to find relative exponents in order to get the critical numbers, right? So you just need to find the derivative. Nobody's going to tell you what technique you need to use to find the derivative. And sometimes there's more than one way you could go about it. I mean, there's always a formal definition, right? There's a limit as h goes to 0. So if I was going to do that on this one, I would say, okay, so then 2 of x plus h plus 3, right? Quantity squared minus 2x plus 3 quantity squared over h. And then I could go through all the math and find the derivative that way. That's one way to find the derivative. But we typically use that method just to prove other techniques so that we can then use those quicker techniques and not ever have to go back to this method. Okay, so method one, before you learned the product rule, method one would have been that you just can multiply this out and then take the derivative. So that it wasn't then it wouldn't be a product anymore. So that would mean y equals, and you would just square out this binomial, right? So that's going to give the first term squared, 2x squared, which is 4x squared, added to multiply both terms together and then times 2. So 2 times 2x times 3, which would give you 12x. And then plus the last term squared, which is 9. Once I have it look like this, it's no longer a binomial being squared, and I can find the derivative, dy dx, or y prime, and I can just use the power rule. So the 4 would stay because that's a constant, coefficient, and then the degree would come down, so it would be 2 times 4, which is 8, and then x, the 2 would go down to 1, so x to the first power. We subtract 1 degree power when we're taking the derivative, plus the derivative of 12x, which is 12, plus the derivative of 9, which is 0. So there's method 1. Just simplify somehow. If you don't have a technique yet to find a derivative, see if you can simplify it and then use the techniques that you do know. Now, of course, your techniques are going to be growing astronomically soon. We're going to learn so many different techniques of finding derivatives. But this method will always work. If you can get it to be something simpler, then do that. Method 2 would be to use the product rule. So the product rule, meaning that this is actually the same thing as 2x plus 3 times the quantity 2x plus 3. Right? So that's two functions multiplied by each other. Just so happens those two functions seem identical, but the product rule will work. So if we're going to use the product rule, we separate our functions out into the two functions that are multiplied. So I'm going to let f of x be 2x plus 3, and g of x would also be 2x plus 3. Okay, then f prime of x is the derivative of 2x plus 3. So the derivative of 2x is 2, the derivative of 3 is 0. And then g prime of x would be the derivative of 2x plus 3, which we just found, and it's 2. So the product rule is it's dy dx equals the first function, which is 2x plus 3, use parentheses around it because it's going to be multiplied by the derivative of the second function, which is 2, added to the second function, which is g of x, multiplied by the first function, which is 2. So also 2 times 2x plus 3. And if we simplify from here, right, using the distributive property, we could say we've got 4 times 2x plus 3, and then using the distributive property, 8x plus 12, which is exactly the same thing that we got using method 1. The third method is what we're going to learn next, and that is called the chain rule. Oops. The chain rule is probably going to be the most common method you use all the time, mixed together actually with other things. We use the product rule, the chain rule, and tomorrow you're going to get the quotient rule. And then, of course, every day you're using that power rule. And then you have to remember all the other things like what's the derivative of the tangent, the sine, the cosine. We haven't done tangent yet, have we? But you will soon. What's the derivative of natural log? What's the derivative of log? What's the derivative of exponential functions? So we really are building up a giant pocket of tools that you can use for finding derivatives. And the chain rule just takes everything all together. Okay. So the chain rule is for if you have a function inside of a function. And do you see that you have that kind of situation right here? You have an inside function, 2x plus 3, call that the inner function. And then you have an outside function, which is you have something that's being squared. So the chain rule function takes care of if you have a function of the form f with another function inside of it. F of g of x, you want to take the derivative of that. So it's for a composition of functions. Next. There we go. So here is how the chain rule works. Of course, you'll go through a proof of this a little bit later, but for today and for now, we just want to practice using that. So you're really good at doing this when you get to BC Calculus or AB, depending on which class you signed up for. So if you want to take the derivative of a function, it works out like this. you take the derivative of the outside part with the inside function still waiting in there to be taken the derivative of, and you multiply it by the derivative of the inside. So I like to simplify chain rule. Instead of looking at it like this, I like to say it's just the outer function's derivative multiplied by the inner function's derivative. Right? And so here was that problem we just had. So the function was 2x plus 3 quantity squared. But if you think about, there's this inside function and then an outside function. So if you could think there's another function inside here. So f of x could be rewritten as it's g of x, which is this function 2x plus 3, quantity being squared, right? So that's a composition. Remember, we did these a couple of times in Math Academy 1, composition of functions, where we would say something like f of x is x squared minus 2x plus 3, and then we'd say g of x is 4x plus 1. Kind of missing the g of x part. There we go. And if we found the composition of the functions, where we would say plug in g of x into f of x, then all the x's in the f would get replaced with the g function. So instead of x squared, I would replace the x with 4x plus 1, and that's what's squared. Don't glitch on me now, Pen. You are not allowed to do this until I'm done with my video. It's glitching, isn't it? It doesn't care what I say. It doesn't care that this is an inconvenient time to not work. Okay, quantity 1 squared minus 2 times 4x plus 1 plus 3. So this would be the composition of the function. All right, so let's practice this then. So again, here's the chain rule. And what we're saying is we have an outside function. We'll call that y in this case. And we have an inner function. We'll call that z. So here's another kind of way to look at chain rule using the Leibniz notation. So we have a function dy dx, which would be finding the derivative of this y of z of x. We want to find that derivative. Well, we could think of it as it's the derivative of the outside function with the z, so in terms of z, so derivative of y with respect to z, multiplied by, now just take the derivative of the z, the inside part, dz dx. So if we take our original problem here, which was y equals 2x plus 3 quantity squared, and then we think, all right, the inside function is z, and you're just going to have to it just takes some practice with this, you guys. You're just going to have to look at these and try to figure out which one's inside and what's the outside, and then think of them separate that way. And then once you get really good at this, and probably very quickly, you're going to stop writing them separate like this. But z is our inside function. And inside of the parentheses being squared, that's z. Z is inside. It's the inner function. And y is the outside function. Okay, so here's y. That's the outer function. All right, so dz dx, right? Z is a function in terms of x. So if we found dz dx, or in other words, the inside derivative, we would get derivative of 2x, which is 2, plus the derivative of 3, which is 0. Okay, then for y, dy, now see how y is a derivative of with respect to z. So dy dz, it's got a variable of z here, would be, well, what's the derivative of z squared, right? Quantity z squared, that's the same thing as just z squared. Well, we would use the power rule in that, which is 2z. The exponent would come to the front, and then the degree would go down by 1. So 2z. And so using this idea of how, let me highlight this part. Using this notation, the derivative of the whole thing, that's what we wanted to find, was the derivative of y with respect to x, would be take the derivative of your outside function, dy dz, and multiply it by the derivative of your inside function, dz dx. I don't think I said this, but I should have at some point pointed it out. If you look at this, you see this dz, if we could cancel it. Why isn't this not working? Come on, pen. Oh, now it works. Just want to stick a dot there. Okay. Pen, work, please. Here we go. Right? And you can see that those dz's would cancel and just give you the dy dx. Okay. We can make it. All right, so then dy, sure, I'll write in red, whatever you want, pen. Dy dx is going to be dy dz, which is 2z, is multiplied by dy dx, which is 2, which gives us 4z. But wait a minute, if I go back here, right, if I say, hey, I want the derivative of y, I want to know what y prime is, and then I say, oh, the answer is 4z, wouldn't that be confusing? Because we just said that y was 2x plus 3 quantity squared, and then I come out and say the derivative is 4z. Because if someone told me that, I would wonder, what are you talking about? Where did the z come from? My function was a function of x. So what that means is when you're done, you just got to go back. Remember, z is this. It's 2x plus 3. You just need to go back and put the 2x plus 3 back into the z, because z is a function of x. I want my finished product to be an answer that is with an x in it, which gives us 8x plus 12, right? We already knew that was going to be a derivative because we did it already 2 other methods. We used product rule on it. We used where you simplify it first. And then we now have done the chain rule to find the derivative. Okay, so let's try another problem using chain rule. Hopefully my pen can make it just a little bit longer for this video. But here, you can actually now find the derivative of this function, y equals natural log of cosine of 2x cubed. Now this is a chain rule problem, but it's going to be using it more than once, the chain rule. Because if you're looking at this right now, you might see you have this overall outside. So it's like you kind of think of it, work your way in. Okay, so start out and then go in, and then you might have to go in again, which means you got to use the chain rule more than once. So overall, the outside is natural log of something, right? So we have an outer function, which is natural log of some other function. And then we have an inner function, which is here, cosine of 2x cubed. The problem is that our inner function is also an outer with an inner, and that happens sometimes, right? So this is also, it's got its own little idea of outer. Its outer is cosine of something, and its inner function is the 2x cubed. So we have this multi-layered derivative going on right now. So we want to find dy dx. Take a deep breath. This is not going to be a problem, I promise. You're going to be okay. All right. So we're going to take first the derivative of the outside. The derivative of the outside would be, it's the first outside, which is natural log of something. And you just leave that something in there. That something will just wait. So the derivative of natural log, right? If I say take the derivative of natural log of some function, let's just say it was x, you'd say, oh, that's 1 over x. Okay, well, now it's going to be 1 over cosine 2x cubed. And you just kind of like ignore that that's not just a 1 over x, but that's how derivative of natural log works. So this is the derivative of the first outside. Okay, Now we need to multiply that by the derivative. Remember, d dx means I'm going to take the derivative of the inside. The inside of this natural log function is cosine of 2x cubed, right? So remember the chain rule. The chain rule is the derivative of the outside times the derivative of the inside. So this is not just outer, this is outer derivative. And this is going to be me taking the inner derivative. That inner has two ends. Let's get that going. There we go. So it's the outer derivative multiplied by the inner derivative. It's just that our inner derivative has on its this derivative of this is also going to require the chain rule. So let's take care of that. Okay, so the process of taking the derivative of cosine 2x cubed will require the chain rule. So the chain rule says take the derivative of the outside. Well, the outside is cosine of some function. So the derivative of cosine is negative sine. And usually it's, we have been finding derivative of cosine x. And so the derivative is negative sine x. And now it's going to be cosine of 2x cubed. So we're going to say the derivative would be negative sine 2x cubed. That's the outside part. And then we're going to multiply it by the derivative of the inside part. So outside with the inside still waiting to be dealt with. And now we're going to deal with it by taking the derivative of it. So we're going to take the derivative of 2x cubed. So this right here, that's the derivative of the inside. This is all going to be multiplied by what we've already done up here, which was the derivative of the outer. So that's there. Okay, so we have, this is the derivative of the outside. This is the derivative of the outside multiplied by the derivative of the inside. The derivative of the inside also had an outer inner. So for that, this is the derivative of the inside's outer part multiplied by the derivative of the inside's inner part. And I still need to take this derivative. So let's put it all together. So y, oops, I'm off pen, sorry. Okay, so y prime is, I'm going to move this over. I just know I'm not going to have enough room. There we go. Y prime is 1 over cosine I just realized I'm not sure why I wrote that's x cubed is supposed to be in there with that. There we go. Did I write it that way up here as well? Let me fix that. I did not. Okay, it was fine there. It's just when I wrote it again. Some reason I wrote it weird. Don't worry, people that bothered by strange pieces of pen written elsewhere. I got your back. I got that erased. We're all good now. Okay. So we have cosine of 2x cubed times, and then times negative sine of 2x cubed, right? Multiplied by, and now I'm going to take the derivative of 2x cubed. Just going to use the power rule on that. So the exponent's going to come down. 3 times 2 is 6, and then x, and then the degree goes down by 1. 3 minus 1, which is 2. Now I'm going to simplify. So I have y prime equals 6. Come on, pen, you can do it. 6x squared there we go. 6x squared negative times sine of 2x cubed over cosine of 2x cubed. And we could even get a little fancier because sine over cosine is tangent. So it's actually negative 6x squared tangent of 2x cubed. And that is using the chain rule. All right, guys, I hope this video helped, and I hope to see you in office hours if you need some help. And yes, chain rule takes some practice. So practice.